Sir, excuse me.
Yes.
The scripts are not clear, sir.
What is still not clear?
Yeah.
Okay, I'll say. Is it okay now? Is it okay now?
Still not, sir. Body is blurred.
Okay. Is it okay now?
Still not, sir. Is it okay now? Body is blurred, sir. Smaller letters can't see.
Small letters, blurred. Is it okay now?
Yes, sir. Now it's okay.
Okay. Okay. തുടങ്ങിക്കല പ്രശ്നം ഇതിലെ വ്യത്യാസം ശരി ശരി അഡ്ജസ്റ്റ്മെന്റ് பண்ணிக்கலாம் All right, so this is what we saw last time, right? Formula for the Rayleigh quotient for the vector xr plus 1, right? Then as a homework, I show you that this one is 0 and this one goes to 0 and so is this and this, right? So because of the nature of the eigenvectors, because we know that the eigenvectors are mutually orthogonal, right? So and orthonormal in particular. So because of that, we see that this one and this one are 0, this one and this one are 0, right? So now we can easily see also that, right? Right, so you know that V1 times A times V1 Hermitian, that is very easy because you know it is V1 Hermitian. A V1 is lambda 1 V1, that is same as lambda 1 V1 Hermitian V1, and because V1 Hermitian V1 is 1, this turned out to be lambda, right? So that is again easier. So now, based on this, you can simplify this, right? So when you simplify this, this is going to be equal to lambda 1 plus epsilon Hermitian times A epsilon over 1 plus epsilon Hermitian times epsilon. So the Rayleigh quotient turned out to be a simple formula, which is lambda 1 plus epsilon Hermitian A epsilon over 1 plus epsilon Hermitian epsilon. So what we can do now is we will try to see the difference between this, right? So I name this as mu r plus 1, right? So that is the Rayleigh quotient. So in this case, what I can do is I can compute mu r plus 1 minus lambda 1, right? So if I compute this, I know this minus lambda 1, right? So that turned out to be lambda 1 plus epsilon Hermitian A epsilon over 1 plus this I can write it as epsilon 2 squared minus lambda 1, right? So I have this mu r plus 1 minus lambda 1 is this, So I can simplify this. Right? So I subtract r, oh, sorry, minus lambda from there. Right? So now this is equal to epsilon Hermitian A epsilon minus lambda 1 minus lambda 1 is gone, right? And then lambda 1 times epsilon 2 norm square. Okay, so you have this. So now you know you want to show that the mu r plus 1 goes to lambda 1 as r goes to infinity. That is what you want to show. So you take the absolute value of this. So that is going to be less or equal to, right, this. Right, so this turned out to be A norm of A times 2 norm of epsilon squared plus absolute value of lambda 1 plus 2 norm of epsilon 2 squared over 1 plus epsilon 2 squared. Right. So now since because norm of epsilon 2 squared goes to 0 as r goes to infinity, right? This one goes to 0, this one goes to 0, this one goes to 0. So eventually the whole thing will goes to 0, right? You know that. Right? So this goes to 0 as r goes to infinity. So that is what we wanted to show. Right? So we wanted to show that the Rayleigh quotient converges to the eigenvalue, leading eigenvalue of the matrix. Right? So now let us compare the rate of convergence in the power method and this Rayleigh quotient method. So I'm going to write a remark here. Okay, so this remark compares the rate of convergence of power method and Rayleigh quotient method. Right? So you can see that in power method, you know that you determine the convergence of KR by using the fact that absolute value of lambda I over lambda 1 is less than 1. So that to the power plus 1 goes to 0, and you basically use that for the to guarantee the convergence of the power method. That is basically the convergence of norm of epsilon 2, right? 2 norm of epsilon in power method. But here we use the fact that epsilon 2 squared converges. In Rayleigh quotient, we use epsilon 2 squared. So you obviously know epsilon 2 squared will converge to 0 faster than epsilon, right? Because if a sequence is converging to 0, then its squared will obviously converge faster. So in that sense, you know that the convergence in Rayleigh quotient is faster than the convergence in power method. Right? So that obviously, you know, Rayleigh quotient is a better way to get a convergence faster. But unfortunately, Rayleigh quotient cannot be computed independently. You have to have power method at R step to get the Rayleigh quotient, right? So at every step, you have to have the power method to get the Rayleigh quotient. So what we do is, usually we do power method at step 1 and then compute the Rayleigh quotient, and then again we compute the power method, and then again we compute the Rayleigh quotient, and we continue like that. So in that sense, we can see that we get the convergence in Rayleigh quotient faster than the power method, right? So that is how we do the Rayleigh quotient problem. So let us see an example for this Rayleigh quotient method. So I will write down the example. Given the matrix A, which is 1, 1, 0, 1, 1 minus 3, minus 3, 8. Right, for this system, right, for this matrix, let us apply power method with Rayleigh quotient to compute the largest eigenvalue of the matrix. So you know at each step you have to apply the power method to get the Rayleigh quotient. So you cannot apply Rayleigh quotient directly. You may need to start with the power method. So I will start with the power method. So I know x naught is 0, 0, 1, right? Then I compute ax naught. Right? So when I compute ax naught, I know you can multiply that. So you get 0 minus 3, 8. So in that step you compute k naught, that is going to be 8. And then once you get k naught, you can get x1, right? Which is going to be 0 minus 3 upon 8 and 1. Once you get this, you get ax1. Right, so ax1, when you compute, you will get minus 0.375 minus 3.375 9.125. So in that case, you get K1 is equal to 9.125. So you keep on continuing computing like this. And so that is how you do power method, right? But here they say do power method with Rayleigh quotient. So what you do is we will do Rayleigh quotient parallelly. So we will compute mu naught, right? So you know the formula for mu naught, that is x naught Hermitian ax naught divided by x naught Hermitian x naught. So this is again matrix multiplication, right? So you know x naught, you know a, so you can write x naught Hermitian ax naught, and you can compute separately, and then you can compute x naught Hermitian with x naught. That is going to be 1 in this case, right? So when you compute this, you know you will get 8. Similarly, you can compute mu1. So that is going to be x1 Hermitian ax1 divided by x1 Hermitian x1. Right? You have an x1 already computed, and you know a, so you can do the computation. Right? So what we usually do is, once we get x naught, we get mu naught, and then we find ax naught, then k naught, and then we go to x1, find x1, then find mu1, right? And then go to ax1, then get k1, then get x2, and then once you get x2, you get mu2, right? In that order, you can do the calculation, or you can first do a few steps of Rayleigh quotient, power method like what I did, and then you started computing the Rayleigh quotient, right? Both ways you can do the computation. So here you will get 9.1096. So and then you can continue working out like this. Right? So what I'm going to do now is I'm going to just write down the answers to see the comparison between power method and the Rayleigh quotient. Right? So this will give you a comparison. Okay, so you know I will get right. So in each step we have a ki and a mu I. So let us write down both of them. So my ki's are going to be 8, 9.125. K2 is 9.1096 approximated value. K3 is 9.1233. K4 is 9.1244 and 5 compute. Right, the mu is this 8. 9.1096 9.1244 right? So these are the calculations, right? So if I go 4 steps, right? So I will get these values for the K's and mu's. So K naught is 8, mu naught is 8. K1 is 9.125, mu1 is 9.1096, and then you can continue like this. So by looking at these numbers, you can see that both of them are in a sense converging to 9.125. This one is also converging to 9.125. So that should be the eigenvalue. You can see that, right? So the eigenvalue is going to be 9.125. So in this example, you can see that even at the third step, the mu I is very close to 9.125. Right? The third step, if you approximate it to 3 decimal places, you will get 9.125, right? But here, you may need to go 1 or 2 more steps to get 9.125 or 9.12, at least 48, right? So if you want to get it up to the decimal approximation, here in Ki, you may need to go for 5 or 6 steps. But in mu, you can see that you almost get close after 3 steps, right? So then that shows you that the Rayleigh quotient method converges faster than the power method. But again, you should understand that without Rayleigh quotient, you cannot do a power method separate. Sorry, without power method, you cannot do a Rayleigh quotient separate, right? So you can always do power method, but for Rayleigh quotient, you need to have power method to get the Rayleigh quotients computed. Right? But anyways, you can do the computation in between each step of the power method. So that helps you to get the convergence faster. And this example shows you everything. So this is about computing the largest eigenvalue and computing it in a faster way, right? So that is what we do in Rayleigh quotient method. Right. So now what we are going to do is you all know that in a n cross n matrix you will have n eigenvalues, right? So in this example, you can see that I have a 3 cross 3 matrix. So I will have 3 eigenvalues. But what I did so far is a method to compute only the first eigenvalue or the largest eigenvalue, lambda 1. So then next what we have to see is we have to see how we can use the same method to compute the other eigenvalues as well, lambda 2, lambda 3, lambda 4, lambda 5, all of them how we can compute, right? So we will see that process of how to compute the other eigenvalues by using this method, and that process is called deflation process. Okay, so this is called deflation process. And so okay, so deflation process is basically a process that tells you how you may apply the previous method, right? So the power method of the Rayleigh quotient to compute the other eigenvalues of a matrix as well, right? After computing lambda 1, right? So that is what we are going to see here. So in order to see this, first notice that you all know that A times B1 is equal to lambda 1 times B1. Right? So that is the definition of eigenvalue and eigenvector. Right? So we all know that. Right? Right? So it is a column vector, you all know. So now what we are going to do is we are going to implement something we studied on the first chapter. Right? That is called elimination process. Right? In the first chapter, we study about two different elimination processes. One is by multiplying an elementary lower triangular matrix, you can eliminate elements below a certain row. Right? So that is what we have studied at the very first section, right? Gaussian elimination. And then again, second part of that you studied about eliminating by using the elementary Hermitian matrix. Right? So you multiply by some h omega to get upper triangular matrix. So in that process, you can recall that every time you pick a column and eliminate elements below the diagonal in that column, right? So that is what you do. So basically you do elimination in every column at each step in theory. So we can apply the same theory here, right? Because B1 is a column vector, so I can apply the same theory here, right? So then there exists a non-singular matrix. Right, so we see similar kind of results especially in the elementary Hermitian matrix theory, right? So you can find a non-singular matrix. There we call it as an elementary Hermitian matrix, but you can always use a elementary lower triangular matrix as well. So this is how you do, right? So multiply by an elementary lower triangular matrix or an elementary Hermitian matrix or some other non-singular matrix to get the column vector transferred into a constant times the first unit vector, that is k0, 0, 0, right? So this one will look like this, k0 and all the way up to 0, right? So this is how this vector will look like, right? So from B you can transfer it into k0, 0, 0. So that is possible, right? So I will write a note here. Right, so you can choose R as some L1 M1, which is an elementary lower triangular matrix, or you can choose R as an elementary Hermitian matrix. So those are the two choices so far you know. Right? So you can think of different other choices as well. So now what we are going to do is we are going to apply this theory here. Right? So now you know A times B1 is equal to lambda times B1. So when you multiply by R, right? So you will have RA B1 is equal to lambda 1 times RB1. Right? But RB1 is KE.
Sir,
Yes.
the board is not clear.
So clear?
Yes. Still not clear, sir.
Yeah. Is it okay now?
Yes, sir. Now it's fine.
Okay. Right, so what you do is you multiply by r. So you get r times a v1 is r times lambda v1. Lambda is a number, so you can put it in front. So what we do is now what I do is I have an identity matrix there, right? A times v1, I can write it as a times I times v1, right? So a times I times v1, I is r inverse r, right? So I just multiply by a r inverse r, which is identity, so there is no change, right? So the reason I do it because both sides I want to get r times v1. Right? So here also I want to get r times v1, which I don't have. So if I want to put an r, I have to neutralize it with an r inverse, which I can do. Right? So here I already have r v1. So in both places I have r v1, so that is basically k times v1. So now you can see that r inverse times k times e1 is equal to lambda 1 times k times e1. Right, so I have lambda 1 times k times e1. Okay, so then k is a constant, non-zero constant, so I can cancel it out, right? So what I have is this r times a r inverse times e1 is going to be lambda 1 e1. Right? So k is a constant. I can cancel out k. So what I did is r inverse times e1 is equal to lambda 1 e1. So the meaning of this is, right? So we talk about this at the beginning of this course in the first chapter. So meaning of this is a matrix multiplied by e1 is the first column, right? So this is the first column of the matrix. The whole thing. The first column of the matrix R inverse, right? So that is equal to lambda 1 E1. So that column is going to look like this, right? So that is going to be lambda 1, 0, 0, all the way up to 0. Right? So this is what theoretically you are going to have, right? Because you can find an elementary Hermitian matrix or elementary lower triangular matrix. So lower triangular matrix is easier than the Hermitian matrix in this case, right? Because finding a lower triangular matrix requires less computational burden compared to the elementary Hermitian. So when I do the example, I will do an elementary lower triangular matrix example. So then you will get this. So this means theoretically this is what I have. So that is what I have is I have R inverse is going to look like this. Lambda 1 I have 0 here. So I have some gamma transpose A1. Right? So where A1 is an n minus 1 plus n minus 1 matrix, and gamma transpose is a row vector with n minus 1 term. Okay, so this is what you are going to have. So you divide the matrix R A R inverse into a block matrix, right? Where the first column, first component is lambda, all the others are 0, right? And then because of the way you divide it into block, you get a matrix of size n minus 1 plus n minus 1. That is 1 less than the size of the original matrix. And then gamma is obviously a column vector. So now what we have to do is we have to make sure that the eigenvalues of A1 are lambda 2, lambda 3 up to lambda n. And because that is what we are looking for, right? So the eigenvalues of other eigenvalues of A, which are lambda 1, lambda 2, lambda 3, and so on up to lambda n. So we have to make sure that they are the same as the eigenvectors of A1. So that is what we are trying to prove. Right, so now because if you want to find the eigenvalues of this R A R inverse, then you want to solve this equation, right? This and so you know that this gives the eigenvalues of R A R inverse. So now we will try to solve this equation, determinant of A minus lambda I. Now you have a block matrix form for A. So what you have is this. So this implies right, so you divide that into equivalent block like the matrix RA R inverse, right? So then lambda I, so it's because you divide one there and the rest here, so you ended up with this. So this is equivalent to this. Right, so you have lambda minus lambda 1, right, times determinant of this is this minus this, right? So determinant of that, so lambda minus lambda 1 or lambda 1 minus lambda times determinant of A minus lambda times In minus 1 is equal to 0. So this gives you this, right? So lambda is equal to lambda 1 or determinant of A1 minus lambda In minus 1 is equal to 0. Okay, right? So what you have is this, right? Eigenvalue. So from this, what you have is the eigenvalues of R, A, R inverse are basically the eigenvalues of A1 and lambda 1. Right? So lambda 1 is one of those eigenvalues, and then others are the eigenvalues of A1. So what's left is you want to show that eigenvalues of R, A, R inverse are lambda 1, lambda 2 up to lambda n. Right? So that is what you want to show. Right? So however, because A is a matrix and Bi and lambda I are the eigenvector and eigenvalue corresponding to A, right? So you have A times Bi is equal to lambda I times Bi, right? So then same argument, right? So you know R A R inverse times R Bi is equal to lambda I times R Bi. Right? So you know the same argument, right, which I did earlier, right? So I multiply by R first and then put an R inverse R in the middle, right? So I do two things together, right? So now this gives me, right, RA R inverse times this, I can name it as Yi is equal to lambda I times Yi. And this is 4i 1 up to n. Right? So same argument, right? So RA R inverse times Yi, because R times Bi is a vector, so I name it as Yi, right? Is equal to lambda I times Yi. Right? So this says the eigenvalues of RA R inverse are lambda 1, lambda 2 up to lambda n. Right? Right? So by this argument, you know the eigenvalues of RA R inverse are basically the same eigenvalues of A, right, which are lambda 1, lambda 2 up to lambda n. So on this side, you say eigenvalues of this matrix are lambda 1 and eigenvalues of A1. But on this side, we have eigenvalues of RA R inverse are lambda 1, lambda 2 up to lambda n. So lambda 1 is common. So the rest should be the eigenvalues of A1, right? So that's clear. Right? So these are eigenvalues of A1. So now what you do is you apply the power method, our Rayleigh quotient method, power method with Rayleigh quotient to A1, right? So when you apply power method to A1, you get lambda 2. Right? So same power method when you apply, you will get lambda 2. Right? And then what you do? Again, you do the same process, right? So again, you apply the same procedure and you will get lambda 3. Right? So again, same procedure, lambda 4. Right? So that is how you can apply this process. So this is called deflation process. Right? So let's do an example of how we can do this deflation process, right? And then we will see a little more about this again.
Sir,
Yes.
it's not clear. Can you say that, however, AVI or AV1?
AVI.
AVI.
AVI is equal to lambda I times VI. And that I is for 1, 2 up to n.
Okay, next line.
Next line, RA, R inverse times RVI is equal to lambda I times RVI.
Okay, sir. So the small letters are not clear. That's
Okay, so I will just do an example and then finish. And then I will put the video in the YouTube again so you can see it again.
okay, sir. Thank you.
So here is A. Right? A is a matrix given as 2, 10, 3, 3, 6, 3, 3, 6, 2, 4, 11. Right, so this is a matrix given. So in order to apply the deflation process, you should have already computed lambda 1 and V1. So given right, so lambda 1 is 11 and V1 is 0.5, 1 and 0.75. Right, so these are computed values. Suppose that all these are given, right? So then what we have to do is we have to apply the deflation process. So the first step is you have to compute the matrix R1 such that R1 times V1 is equal to some K times this, right? So what I am going to do is to do this, right? So this is elementary permutation matrix P21, which we studied at the very first section, right? So that you all know when I multiply by P21, I get the rows interchange. So I have 1, 0.5 and 0.75. Right, so I do that because it is easy for me to write down the elementary lower triangular matrix. Right, so if I make 1 there, then my elementary lower triangular matrix is easy to compute. But you don't need to do that. You can still keep it as 0.5, 1 and 0.5, but then you have to do a lot of divisions. Right, so here I can save the division by doing this. So now what I do is I choose my M1, which you learn in chapter 1, 0, 0.5 and 0.75. Right, so that is 35. I interchange the rows. Right. So then you know that this. right? So when you multiply by this element below triangular matrix with this one, you get 1, 0, 0. You know how to do it by what you learned in the first chapter, right? So this is what you have, right? So now what you do is you have to compute this, right? So your R1 is L1 M1 times P21. So what you do is you multiply by R1 A R1 inverse. Right, so you multiply by R1 A R1 inverse. So that you all know R1 is this, L1 M1 P21 A, R1 inverse is the other way around, right? So P21 and L1 of minus M1. Right? So this multiplication you can do, right? Because you know what is P21, you know what is P21, you know what is the matrix L1 M1, you know what is the matrix L1 minus M1, right? So all this you know, right? So you can do the multiplication, right? So I am not going to show all the multiplications because it is just writing down the matrices and multiply them together, right? So take A, multiply by P21 in front and P21 in behind, and then L1 M1 in front, and after that multiply by L1 minus M1 from behind. So once you do that, you will get a matrix. So that matrix in this example is going to look like this. So once you do the multiplication, once you finish doing the multiplication, you will get a matrix which look like this: 11, 0, 0, 10 minus 3 minus 4.5, 4, 0, 8. Right? So that should be that is going to be the matrix. Right? So in this case, now you can see what is your A1. So your A1, so this work has nothing to do with what you learned today, right? So it is about this exercise is more about only the theory part is what you learned today. Computational part, all these you learn on the first chapter, right? So it is basically a repetition of what you learned in the first chapter. So then your A1 is going to be this matrix: minus 3, 0, minus 4.5 and 8. So this is what you have here. So now what you have to do is you have to apply the power method for this matrix, right? But fortunately, you don't need to do this, right? Because so theoretically you have to apply the power method here, right? To get lambda 2. But here you can get lambda 2 and lambda 3 without doing anything because this is an upper triangular matrix. Because A is upper triangular, A1 is upper triangular, the eigenvalues are diagonal terms. So the eigenvalues of a upper triangular matrix or a lower triangular matrix or a diagonal matrix are always the diagonal terms, right? even if you write this as A minus lambda I and so on, you still get minus 3 and 8 as the eigenvalue, right? That is a special property of triangular matrices, including diagonal matrix. So in this case, you know that the diagonal terms are your eigenvalues, so you can directly write down the eigenvalues without applying the power method. Right? Otherwise, you are supposed to apply the power method. So in this case, you know that, you know, lambda 2 is the biggest one, so that is 8, and lambda 3 is minus 3. So those are the other 3 eigenvalues. So this is how you can do the computation in deflation process, right? So where you apply the techniques which you learn on the first chapter to the theory which you studied here, right? So this is basically a combination of first chapter and this, right? So this is how you compute the other eigenvalues of a matrix, right? So in the next class, I will give you one more example of this, and then we will talk a little bit more on this deflation process, and then we will talk about how to improve the results which we find in this chapter so far, right? So that is what we are going to learn. That we will see on Monday class. Right? So I will stop here and then continue